Hello everyone, my name is Dr. Muhammad AIT ALI. I'm part of a research team where we work on mechanical engineering problems in manufacturing and in fluid dynamics. Me and the co-authors all work in Mohammedia School of Engineers, part of Mohammed V University of Rabat. I am happy to present this fifth international conference on renewable energies for developing countries, known as Redec 2020. This work is titled Analytical and Numerical Study of an Oscillating Liquid inside a U-tube used as a wave energy converter. The points that we will cover in these presentations: after the introduction, we will describe the analytical analysis of the oscillating liquids inside the fixed U-tube. Then in this next section, we will present a numerical study of the same motion using a volume of fluid methods. And in both cases, we conduct parametrical study, and we will present our main conclusions and perspectives. Ocean energy is one of the many renewable energy sources that can be relied upon to reduce or solve some environment problems. The work of Gunn gives an estimation and a method of estimation of this power source available worldwide. As we can see in this figure, countries with access to this power can evaluate this energy. A global evaluation of this energy is estimated to be up to 2.3 terawatts of power, which is huge and could solve a lot of problems. To capture this energy, many wave energy converters exist. One way of classifying these energy converters is according to their direction of incidence of the incidence of the wave. We find that there is the terminator category, where converters are perpendicular to the wave direction, as we can see in figure 2.2a. There is the attenuator category of converters, which are parallel to the wave direction, as we can see with these red converters in figure 2b. And we have the point absorber category of converters which have no discernible direction. In this work, we are studying a converter of the second category, attenuator wave energy converters, that is a U-tube partially filled with water. The principle of this device is to convert the kinetic energy of the waves by animating the liquid inside the U-tube. In this figure, we can see a schematic representation of multiple U-tubes chained together to produce more power. To our knowledge, the principle of this device was mentioned first by a patent of Scarp in 1976. A remarkable work of an elaborate setup was proposed by Cho et al., they aim to maximize the output by matching the liquid's oscillations to the wave's frequency using an analytical approach. A different use of this principle of the U-tube's liquid's oscillation is found in structural engineering, where they use it to suppress the structure's vibration, and they refer to it as bi-tuned liquid column dampers. So the goal of this work is to study the dynamic behavior of an oscillating liquid inside the U-tube with open ends, then to develop a realistic analytical and numerical model to estimate the potential power that could be extracted for our specific geometry. In this section, we will conduct an analytical analysis of the oscillating liquid inside the fixed U-tube. Our geometry is a U-tube with a square section. H, the parameter H, is the instantaneous position of the free liquid surface relative to the equilibrium position. To develop the equation of the governing the liquid motion, we used the non-stationary Bernoulli's equation, and we took into account the friction between the liquid and the inner surfaces of the U-tube, and we took also into account the pressure loss due to the 19 degrees bends of the U-tube. We obtained this nonlinear equation where h2 points is the acceleration of the free liquid surface, and h point indicates the speed of the free liquid surface. The solution of this nonlinear equation is an oscillatory movement with a dampening effect. The natural period has this expression. To estimate the available power for extraction, we use this formula where it is the flow rate multiplied by the atmospheric pressure in the part where there is only air. To solve this nonlinear equation, we use MATLAB's function ODE45. In the left figure here, we have the liquid's free surface position with respect to time. We see that it is an oscillatory motion with a dampening effect. In the right figure, we have the power available for extraction generated by the liquid's motion. In the first peak, we have about 1.6 kilowatts. In the second peak, subsequent peak power, we have only about 1.4 kilowatts. In the following sections, we use these two quantities, which means the first peak power and the subsequent peak power. We use these two quantities to characterize the performance variation of this energy converter. We consider this configuration with these parameters as our reference configuration to which we will compare all the following studies. We conducted a parametric study of the effects of geometrical parameters on the power produced by this converter. Each time we changed a parameter, we kept the others fixed, and we compared the results to the reference configuration mentioned in the previous slide. First, we decreased only the horizontal length of the U-tubes from 560 to 230 millimeters. In this decrease, when we decreased this parameter, we observed an increase of the first power peak by 11% and a smaller increase of the subsequent power peak of only 7%, which indicates a slight increase of the dampening. Second place, we increased the hydraulic diameter from 126 to 300 millimeters. We observed a huge increase in the first power peak by 467%. We then decreased the hydraulic diameter to 100 millimeters. We observed a decrease of 7%. In all cases, the dampening of peak power stayed the same when we changed the hydraulic diameter. We then changed the head loss coefficient K due to the 90 degrees elbows of the U-tube, which is equivalent in reality to changing the elbows geometry. So we increased the head loss coefficient from 1.13 to 11.3. We observed a 30% decrease of the peak power and 61% decrease of the subsequent power peak. Then we decreased the head loss from 1.13 to 0.01, which indicates a very small head loss coefficient. We observed an increase of only 7% of the first peak power, and the dampening of the peak power is very small, as we have only, as we see here, the first peak power to 1.7 kilowatts to 1.7, though slightly, and we observe no reduction, though very small dampening. In this section, we present the numerical simulation of the liquid's motion inside the U-tube using fluent ANSYS. The reasons behind this simulation is to make fewer assumptions to get a more realistic evaluation of the device's performance and to compare its results with those of the analytical model. We developed a 3D transient dynamic simulation using the volume of fluid method with implicit formulation. We used the multi-phase formulation, which includes air and water, and we used the K-epsilon turbulent model and about 45,000 linear hex elements as a mesh for both domains. As a result, we observed that there is a solution of the free surface, which will influence the precision on the free surface position. We extracted the free surface position and computed the power available for extraction. We observed only a 3% difference in of the natural period, but we have a 10% difference between the subsequent power peaks, which gets us to conclude that the analytical model underestimates the dampening. We then studied the effect of the simulation parameters on the results. We changed the mesh type from linear to quadratic and the model formulation from implicit to explicit, and we changed the mesh size by changing the element's edge size from 15 millimeters to 3 millimeters. In all these cases, we observed that we have no noticeable effects or very small changes in the subsequent periods. As a conclusion of this work, we established a detailed liquid's motion equation inside the U-tubes used as wave energy converter. We showed that the peak power is about 1.6 kilowatts with 12% dampening for our geometry. We used this analytical model to conduct a parametrical study. We decreased the U-tube's horizontal length. We showed that it increases the power peak. When we increased the elbow's head loss, we reduced the peak power by 52% and the dampening. But when we increased the hydraulic power, we increased significantly the peak power with about up to 400%. Then we developed a more realistic numerical simulation using the volume of fluid methods, where we observed sloshing, and the results of this model were in very good agreements with the analytical model. Both approaches helped us to have a good understanding of the U-tube's parameters' effects on the results. As a continuation of this work, we can now, using this model, simulate more complex configuration. We look forward to validate experimentally different conclusions, and we hope to study the interaction with the ocean's waves and the energy converter to see how we can optimize the outcome of this work.